All right, so let's take it another extreme here. Let's do glass and air. I'm gonna make this angle, it's coming, so it's starting off at the crown glass. So 1.52 is the index of refraction. Air, roughly 1. And I'm gonna make this angle 60 degrees. This light comes this way, and then it should, there. And we'll call this theta 4. So I have 1.52 times the sine of 60 degrees.
What is this, the air flux?
Equals 1 times the sine of theta 4. What is theta 4?
Air is 1.
Air is 1, yes, index fraction of air. Close enough to 1 to count.
Calculator says it doesn't like that equation.
Yeah.
I got 131.6.
We got a fourth quadrant angle, or second quadrant angle, which would put it over here.
Yeah. 131.6.
If you got 131 for the,
It's like 1.316 is 1.52 times sine 60.
so it's the arc sine, 1.316.
Divided by 1.
All right. I was expecting you to get an arrow.
Yeah, I got an air.
The sine of an angle cannot be bigger than 1, so the fact that I'm doing an arc sine of something bigger than 1 is an issue. And so what that means is that the light doesn't actually escape.
So, Ronald was right, it just goes back.
Yeah, it would reflect in. Now, there is that critical angle at which when the light hits it, it's now gonna just sort of shoot along here. This is known as total internal reflection. And so, let's actually figure out what that angle is, that critical angle. So I'm trying to find the angle at which the light's just gonna shoot right along the edge. This is my theta 1, this is N1, N2. N2 is less than N1, and that is a 90-degree angle right there. So I plug into Snell's law. So N1 sine of theta 1 is equal to N2 sine of 90 degrees. And so sine of, this is the critical angle, so I actually could label that as theta sub c. Sine of theta sub c is N2 over N1. What's the sine of 90 degrees?
One.
And so we just left with N2 over N1. And so my critical angle is N2 over N1, arc sine of N2 over N1. So in the case of crown glass and air, that critical angle happens at the arc sine of 1.0 over 1.52.
We got 41 40.13.
Okay, 41.139
Nine, sorry.
degrees, presumably. And so anytime you're going from a higher index of refraction to a lower index of refraction, you do run the risk of the light not actually escaping. And that's the essence of fiber optics. As long as you don't have a kink in the optic cable, you shine the light in one end and just basically bounces off the sides. All right, questions up to here? All right. Oh. Now the textbook has one other bit on apparent depth, so let's just sort of go through that. There are some assumptions that they make in their derivation, and sort of address that also. So I have some substance down here. I think it's helpful just to think of it as I have water here, and I'm looking at it from the side. And basically, my brain processes things as if light always travels in a straight line. Because for the most part, it does for most of the things I do. Now, if I have an object here, what's this? I have a fish or something's under the water. The light that's bouncing off of it's going to hit here, and then it's going to then bounce into my eye. Bounce, refract. I don't think I actually use that word. It's going to refract into my eye. But to me, my brain is going to process it and think that the object is here, not where it actually is. So we have the actual depth here, which I'll label as P, and then we have an apparent depth here, Q. Again, using P and Q in the same sense as we did before, the fact that P is the distance from the surface to where the actual object is, and then Q is the distance to where the image is. Need to establish some angles here. So this angle right here, from the vertical to where I think it is, which basically would be the same angle as that, is theta, just to keep track, step with my notes, theta 2. The actual angle here, theta 1, which would be the same angle as this angle right here, that's also theta 1. And I have two right triangles. I've got the smaller right triangle, so I've got the right triangle here, where that is theta 2, and this length here is Q. And then I have the larger one, where this is P, and this is theta 1. Now they do have one thing in common, is the fact that this distance right here is the same. That's this part right here. That's the same for both of them. So let's give it a label of X. That's theta 2 there. So I know the tangent of theta 1 is opposite over hypotenuse, so that's X over P. And the tangent of theta 2 is equal to x over q. And so then the book makes, so all that is true regardless, there's no assumptions really being made here, other than that light travels in a straight line and refracts. They then make the assumption that, assume that Q is much greater than X and P is greater than Q. If we say that Q is much bigger than X, what do we know about that fraction then? If Q is much bigger than X,
It's very small.
and therefore small angle approximation can be used. So tangent to theta, this would be approximately equal to the sine of theta 2, and this would be approximately equal to the sine of theta 1. Isn't that convenient? We've got sines again. Snell's law uses sines. So solving for x, I have x is equal to p sine theta 1. And from down here, that's equal to q sine theta 2. If I look at the light outside and light inside, I have theta 1, theta 2. Oops. That's not theta 2. I lied there. That's theta 2. Sorry about that. Because this would be the complement of theta 2. That's the complement of theta 2. That's theta 2. It doesn't change anything we've written other than that. Now it affects.
Wait,
Because-
would that mean that theta 2 is equal to theta 1?
No, because this straight line right here is this straight line right there.
Oh, okay, okay.
Trying to trick the system.
I've made so many stupid errors in the past couple of days that I wouldn't be surprised if I drew theta 2 wrong there, but this time I'm pretty sure I drew theta 2 correctly. From Snell's law, I know that sine of theta 1 is equal to n2 sine theta 2 over n1, which is equal to q sine theta 2. Conveniently, we now have sine of theta 2 showing up twice. Boom, boom. And so I have a ratio here of my indices of refraction, n2 over n1, is equal to q over p, where n2 is less than n1. Ooh,
How did you get the n theta, or yeah, sorry, the n2 over n1?
all right, so basically if I look at the blue line here, so think about that light is coming in from one medium, this is the path that the light's taking, and then it refracts when it comes to the outside. This is basically the problems we had been doing with light bending.
Bending.
I have the angles with respect to the verticals, and so classic just applies Snell's law.
Okay.
So from here, divide by n1, so sine theta 1 is equal to n2 sine theta 2 divided by n1, which is what I wrote here.
Okay.
So it does assume enough depth there in order to be valid. If it's something shallow, I guess the book just doesn't care. You can't make the small angle approximation then, it's just more complicated. More information would have to be given. Questions?
Next time I go bow fishing, that's all I'm gonna be thinking. Alright, well, it's here, I'm seeing it there, and I need to go here.
Right on. I mean, that's,
So would you
and yet
do,
again, physics comes back around to violence. Or hunting, whatever you wanna call it.
The shunting.
Sorry, Ronald, you were saying?
So if you out in the river and you see a fish and he's swimming at a certain depth, you know that if you want to kill it, you have to shoot it a little bit farther or closer. All depends what the
Yeah.
the distance is.
You target or below it.
Yeah.
And that's gonna be true even if it's shallow, just that if it's shallow, it's less of an issue.
The further deep you go, the more below you gotta go.
Yeah.
And index of refraction of water of, I guess that's fresh water in there, is 1.33, and so
Salt water is more buoyancy though.
it does. I don't know how that affects the index of refraction though. Those are two separate qualities.
It
But-
does or it doesn't affect the index of refraction?
So
I
would
don't
you have
know.
to add salt to it?
Well, probably would affect it. If I had to guess.
I mean, you are adding another element there, so, I mean, salt is a crystalline structure. At some point, we'll look up salt water, but in fresh water, that if it's deep enough, basically P is gonna be roughly 33% farther down than it appears.
But I'm sure that depending on where you are in the ocean, the amount of change from one sea to another sea probably is different, because there's, like, the Black Sea has more salt in it than, say, the Red Sea, so.
Seawater is 1.398, or freshwater is 1.389.
Oh, they have a different number than the book does.
Imagine that.
I've been doing 1.33 all this time. They lied.
What was the, index of refraction for saltwater?
1.398.
Yeah. It's a little different, but.
Which,
Oh,
does it put it closer to, puts it closer to glass?
it says that the refractive index of water is actually a function of the wavelength of the light as well as salinity, temperature, and pressure of the water.
Yeah, it depends on how sophisticated you want to get. It does, the index of refraction does vary with the wavelength. That's, I mean, if you ever seen a prism, light comes into the glass and then bounces around and comes out as a rainbow, that's because different wavelengths are traveling at slightly different speeds. I was not worried about that. If you make corrective lenses, please take that into account. All right. Any other questions, comments, concerns? All right. That's chapter 35 right there. I'm not trying to rush through it, I'm just, there's just not as much. They have fewer topics in more chapters. All right, so this obviously relates to it. If I have, because we can now have, we have a method for making light bend, we can now create lenses, either for glasses or contacts or telescopes, binoculars, whatever you need to have to have it. Now, if this were the full 16-week course, and this is just to make you jealous that you're not taking the full 16-week course, I would derive the next equation. And judging by the enthralled looks from previous students, I'm sure you were jealous. They were so enthralled, they were speechless.
I'm speechless at this chapter title, this subchapter title. It says, is seeing the same as believing? What does that even mean?
Well, it's kind of like apparent depth. I see the fish there, but do I really believe the fish is there? All right, so if I have a lens here, so let's imagine that I've got a piece of glass that sort of looks like that. Now, the classic thin lens problems that we'll get into next after this, there's a certain symmetry involved, and there's some symmetry here too, but the focal length of this system here, so light comes in, it's going to bend, at least draw that part.
Is that lens rounded on the back, or is that supposed to be flat?
They're slightly rounded on each side. And I'm gonna see how well I can draw right now. I'm trying to make the curve on the back side here to be different than the curve here. So light comes in. When you think about the index, the fact that light will refract as it enters, just go ahead and state this is air, this is some sort of glass or material. The index of refraction is based upon,
The curvature.
yeah, so you basically draw a tangent line, that's the surface that we're dealing with here. Perpendicular to that. That would be perpendicular to the curvature at that point. And so this would be the angle of incidence. This is the angle coming in. Theta 1 in the first example I did. It is going to bend closer to that vertical. And then it's going to hit the other side. So light's coming in straight. It's going to bend, and then we have a new surface here. I draw the tangent line. That's supposed to be perpendicular to my tangent line. And so I have a new angle of incidence here. And it's going into a smaller index of refraction, so it's going to bend farther away from the middle. And so basically the light's going to come in and take that path. If I've got symmetry about it, I'm going to attempt to draw some symmetry. Let's just establish a sort of middle axis. Light that comes in parallel, equal distance below the axis as above the axis. Tangent line there, got my line perpendicular to that, and so light comes in, it's gonna bend, it's gonna hit the surface over here. And then away, and so we get the point where the two lights meet